Welcome dear students in the third video of laws of motion. In this video I am going to explain about linear momentum and Newton's second laws of motion. So first let us start with linear momentum. So what is linear momentum? Linear momentum of a body is the quantity of motion contained in the body. This linear momentum depends on the mass of the body and the velocity of the body. So we can define this linear momentum as linear momentum is the product of mass and velocity of the body. That is, we can write linear momentum is equals to mass into velocity, or this linear momentum is denoted by P. P is equals to mv. Linear momentum is a vector quantity because it is the product of mass and velocity is a vector quantity. The direction of linear momentum is in the direction of velocity of the body. Let us see the SI unit of linear momentum. As the linear momentum is the product of mass and velocity, so mass of a body is measured in kilogram and velocity is measured in meter per second. So SI unit of linear momentum is Kg meter per second. If we will talk about its Cgs unit, so mass is measured in gram and velocity SI unit is centimeter per second. So we can write gram centimeter per second. This is about linear momentum. Now let us talk about Newton's second law of motion. According to Newton's second law, the rate of change of linear momentum is directly proportional to the force applied, and the change takes place in the direction of applied force. This Newton's second law gives the mathematical expression for force, or we can say Newton's second law gives the measurement of force. So let us see. Let a body of mass small m moving initially with velocity u. A force F acts on the body in the direction of motion. This force acts for time t. Due to this force, the velocity changes from u to v. Now, if we will calculate its initial linear momentum, means in the first state what was its linear momentum, so we can write product of mass and velocity. Similarly, if we will find its final linear momentum, so we can write mass into velocity. Now, what is the change in linear momentum? So change means final minus initial. So we can write mv minus mu. It is the change in linear momentum. In Newton's second law, I said rate of change of linear momentum. So we will find rate of change of linear momentum. So rate of change of linear momentum means change in linear momentum by time. This is called the rate of change of linear momentum. Now, according to Newton's second law, as it is said, rate of change of linear momentum is directly proportional to the force applied, or we can write it as mb minus mu by, we can write it as F is directly proportional to mb minus mu by t, or F is equals to, so I remove this proportionality symbol, so we will use a constant for that k. M we can take common from here. So we can write V minus U by T, where K is a proportionality constant. V minus U by T, we know this is acceleration, so we can write F is equals to kma, where V minus U by T is called the acceleration of the body. The value of K depends on the system of unit used to measure the force. In Cgs system and in SI system, the force is measured in such a way that the value of K we get always 1. So as K is equals to 1, so we can write F is equals to ma. This is the measurement of force, and we obtain an expression for force from Newton's second law of motion. Now let us see the Cgs and SI unit of force. As we got the mathematical expression or measurement of force from Newton's second law, that is F equals to ma. So now see the SI unit. SI unit of force, mass is measured in kilogram. So we can write kilogram, and acceleration SI unit is meter per second square. So kg meter per second square is the SI unit of force, or we can write it as Newton or Newton. So Newton is the SI unit of force. Now what is 1 Newton? So see, force, so we can write force is 1 Newton, mass 1 kg, and acceleration 1 meter per second square. So 1 Newton is the force which, when acts on a body of mass 1 kg, produces an acceleration of 1 meter per second square. So this is 1 Newton. Similarly, if we will talk about its Cgs unit, so see, Cgs unit of force, mass is measured in gram and acceleration is measured in centimeter per second square. So gram centimeter per second square is the Cgs unit of force, or we can say it as dyne. Now similarly, as we have defined 1 Newton, similarly we can define 1 dyne. So 1 dyne is a force which, when acts on a body of mass 1 kg, 1 gram, produces an acceleration of 1 centimeter per second square. So 1 dyne is the force which, when acts on a body of mass 1 gram, produces an acceleration of 1 centimeter per second square. Now let us see the relation between SI and Cgs unit of force. As we have seen, 1 Newton is equals to 1 kg into 1 meter per second square. So let us convert these units in Cgs. So we can write 1 Newton is equals to 1 kg is equals to 1000 gram into, here 1 meter we can write it as 100 centimeter per second square. So 1 Newton is equals to 1, 2, 3, 4, 5. So 10 to the power 5 gram centimeter per second square, or we can say 1 Newton is equals to 10 to the power 5 dyne. So this is the relationship between SI and Cgs unit of force, that is 1 Newton equals to 10 to the power 5 dyne. Now let us plot some graph. So graph between force and mass. Force and acceleration, and mass and acceleration. So we will plot now three graphs. So let us see one by one. So first I am going to show the relationship between acceleration of the body and the applied force. As we know, a large force acts on a body, then acceleration will be also more. It means the force produced in a body of a given mass, that is mass is constant. So I said the acceleration produced in a body of given mass is directly proportional to the force applied on it. So we can represent it as, suppose this side I am showing the acceleration along y-axis and this side I am showing the force along x-axis. Keeping the mass of the body as a constant. So mass is constant, m equals to constant. So we will get a graph which varies linearly, means more the force, more will be the acceleration. So it varies linearly. Next graph we will see between force and mass, keeping the acceleration of the body as a constant. So we will represent along y-axis, we will show the force, and along x-axis we will represent the mass of the body. So this side mass, and keeping a equals to constant, means acceleration of the body is constant. So what we will find here, if we will draw the graph, the force needed to produce a given acceleration in a body is directly proportional to the mass of the body. So we can get a graph like this. It is also directly proportional. Mass will be more, we have to apply a larger force. Next, one more graph we can see, the graph between mass and acceleration, keeping the force as a constant. So for this, again along y-axis and x-axis, two axis we will take, and along the x-axis we will take mass, and along this we will take the acceleration of the body, keeping force as a constant. So look at this, force is equals to mass into acceleration. So we can write here a, or we can write m equals to f by a. Keeping force constant, mass and acceleration varies inversely, means if more will be the mass, acceleration produced by the force will be less. So we can get a graph like this. It means as the mass is increasing, acceleration is decreasing. So these are the graphs we have just seen, and we draw that graph, we obtained this graph from the relation F equals to ma. Now Newton's second law is actual law of motion, or we can say it is the real law of motion. It is because second law contains first law as well as the third law of motion. Let us see, or let us obtain Newton's first law from second law. So children, as we got an expression F equals to ma, if force equals to 0, so what happens? This we can write ma equals to 0. Now if force is not acting on a body, we know that mass never zeros. It means acceleration is 0. Acceleration 0 means the body, if the body is in rest, it remains in rest. Without the application of force, there will be no any acceleration in the body. Or if the body is moving with a uniform velocity or uniform motion, the velocity cannot increase or decrease till the force is not applied on the body. So we can say, as we know from Newton's first law, a body at rest remains at rest, or a body in motion along a straight line continue its motion until and unless an external force is applied on it. Now let us see some examples of second law of motion in our daily life. Before that, let us remind the second law of motion. As I said, according to Newton's second law, the rate of change of linear momentum is directly proportional to the force applied, and the change takes place in the direction of applied force. And we have seen that force is equals to change in linear momentum. So we get it as change in linear momentum by time, which is called the rate of change of linear momentum. Or we can write it as F is equals to P2 minus P1, where P2 is the final linear momentum and P1 is the initial linear momentum by time. Or we can write it as F is equals to del P by T, where del P represents change in linear momentum and T is the time, F is the force. So we can just find in this, if time taken is more, then force will be less. See some examples about that. It means while catching a ball, the cricketer withdraws his hands along the ball, or he pulls his hand in backward direction. By doing so, what he did, he increases the time. As the time will increase, the change in momentum take place in more time, so effect of force will decrease and the cricketer will receive less injury in his hand. That means one more thing we can see, or other examples we can talk about that. An athlete often lands on a sand or foam. Why so? When he is taking a long jump. The reason behind that, when he jumps on a sand, he pushes the sand little in the direction of force. So time increases. As the time increases, force decreases. More example if we can talk, glass vessels. When the glass vessel falls on the cemented floor, it breaks. The reason is that on the cemented floor, the time to change in linear momentum is very less. Means rate of change of momentum takes place very fast. Means force applied is more and the glass vessels break. On the other hand, if the same glass vessels falls on the sand, it does not breaks. The reason is that on the sand, when it falls, the time increases. The glass vessels comes to rest. Glass vessel does not comes in rest suddenly. It takes time. So time increases, force decreases. Another thing we can say, if we will talk about del P is equals to force into time, means change in momentum can be obtained either by applying a small force taken in large time or large time taken in small, applying a small force. Like when we hammer a nail So we are applying a large force for a small time. So force is more, time taken is less. So change in momentum takes place. Large change in momentum takes place in a small time by the application of a large force. Similarly, when a cricketer hits the ball from his bat, the time in hitting the ball is very less. This time is less and force applied is more. So large change in momentum takes place in a small time. So these are all examples of Newton's second law in our daily life. This is all about linear momentum, Newton's second law, expression for force and some real life examples. Thank you students. Thank you for watching.